In this video, I'll give you an example of how to solve a first-order non-homogeneous recurrence relation using generating functions. So the recurrence relation we're going to look at is this one. So I let f of 0, f0 be 2, and then for n at least 1, we have that fn is equal to 3 times fn minus 1 plus 3 to the n minus 1. So we would like to prove this using generating functions. The way to do that is to start by just writing down a generating function for the sequence. So let f of x, where x is a real variable, be the sum n equals 0 to infinity f sub n x to the n. Okay. The trick here is, suppose I write down my recurrence relation. What I can do is multiply both sides by x to the n. When I do that, on the left side, I get something which is sort of like the summand in my f of x. So I get f of n x to the n, and then I need to multiply everything on the right side by x to the n as well. So I get 3 times f of n minus 1 times x to the n plus 3 to the n minus 1 x to the n. Now on the left side, this is, like I said, basically giving me the summand of my generating function. It's giving me fn x to the n. And to get the function f of x, what I can do is sum this over all n, but I have to be a little bit careful here because my original equation is only valid when n is at least 1. So in order for this to be valid, I can only really sum this over all n, which is at least 1, because this equation only holds when n is at least 1. It doesn't hold for n equals 0. In particular, if I let n equals 0, I would have an f sub n minus 1, which would be an f minus, sub minus 1, which doesn't even make any sense. So we sum this over all n at least 1. So n equals 1 to infinity, fn x to the n equals 3 times, so this is n equals 1 to infinity, f sub n minus 1 x to the n plus sum n equals 1 to infinity, 3 to the n minus 1 x to the n. So now the next step is to write this expression in terms of f of x, which is the function I defined at the beginning, and other generating functions we are familiar with. So what do I mean by that? Well, for example, on the left side, we have the sum n equals 1 to infinity of fn x to the n, which is pretty much the same thing as f of x, except that you're missing the n equals 0 term. So on the left side, what you have is f of x minus f0 x to the 0, because f of x is this, which sums from 0 to infinity, and what we have here is the sum from 1 to infinity. So it's the same as f of x, except it's missing the 0 term, so we can just subtract it. Here, what we have, so what I'd like to do is to make the subscript here the same as the exponent here, just to make it a little bit more similar to f of x. So to do that, I can factor out an x like this, okay? And we're still going to deal with this a little bit more. We'll simplify it more in a second. But let's look at the third term. And again, I can factor out an x, and I get the sum from n equals 1 to infinity, 3 to the n minus 1 times x to the n minus 1. Okay, so now I'm pretty happy with the left-hand side of this equation. But on the right-hand side, I've still got these infinite sums, which I would like to simplify. So for the first sum, what I can do is say that, well, if I sum from 1 to infinity fn minus 1 x to the n minus 1, that's the same as f0 times x to the 0 plus, because if I plug in n equals 1, this is what I get. If I plug in n equals 2, I get f1 x to the 1, f2 x to the 2, and so on. And you can see that if I kind of shift the index a little bit, what I end up with here is the sum n equals 0 to infinity fn x to the n. And lo and behold, this is just equal to f of x. So that kind of takes care of this sum here. Now what about the other one, the thing involving the 3 to the n minus 1? Well, I can again change the indices to write this as the sum n equals 0 to infinity, 3 to the n, x to the n, and then we can recognize that this has this is one of our kind of very familiar generating functions. So maybe if I do this in 2 steps, I can say let y be 3x. Then I get, this is the sum n equals 0 to infinity yn, y to the n, which I can then say is 1 over 1 minus y, which is the same as 1 over 1 minus 3x. So that takes care of this sum. So now if I substitute this into my equation, what I have is that f of x minus f0 x to the 0 equals 3x f of x plus x times 1 over 1 minus 3x. Now if we think back to the original problem, remember we were told that f0 is 2. So we can plug that in. So what we get here is that f of x minus 2 is 3x f of x plus x over 1 minus 3x. So now what I want to do is solve for f of x. So what we get now is that if I pull over this, so I'm going to put all the f of x's on one side and factor it out. So I get 1 minus 3x here equals 2 plus x over 1 minus 3x, okay, which is the same as if I combine these two things on the right-hand side, it's 2, so I'm going to multiply the top and bottom of 2 by 1 minus 3x, so it's 2 minus 6x plus x over 1 minus 3x. And so what we get now is that f of x is equal to 2 minus 5x over 1 minus 3x squared. And this is good news because this is something we can understand in terms of our kind of standard generating functions. So remember that 1 minus 1 over 1 over 1 minus x squared is the sum n equals 0 to infinity n plus 1 x to the n. And we can use that here. So using this, I can say that 1 over 1 minus 3x squared is the same thing as the sum n equals 0 to infinity n plus 1 3 to the n x to the n. So now this tells us that f of x is, if you think about it, so it's f of x is 2 over 1 minus 3x squared minus 5x times the same thing. And if we kind of substitute this sum into both of these, this expression above into both of these things, you get that this is equal to the sum n equals 0 to infinity 2 times n plus 1 3 to the n x to the n, and then minus 5x times this sum. And when I take the 5x inside, what it does is it raises the power of x by 1. So it becomes an x to the n plus 1. And now what I would like to do is to combine these two sums. But if I want to combine them kind of term by term for each power of x, I need the powers of x to be the same. And here I've got an n, and there I've got an n plus 1. So I need to shift the exponents, or what I should say is I need to shift the indices of the second sum. So if you think about what happens, if I start the sum at n equals 1, then what I get is 5n 3 to the n minus 1 x to the n. If I take off the first term of the first sum, the n equals 0 term, I have that it's 2 times x to the 0, which is just 2, plus the sum n equals 1 to infinity of 2n plus 1, 3 to the n, minus 5n 3 to the n minus 1, all in brackets, times x to the n. Now remember we said that f of x is the same as the sum fn x to the n equals 0 to infinity. And now we've proven that f of x is equal to this. So what this tells us is that f of 0 is 2, which we already knew because that was our initial condition, and that for n at least 1, f of n is equal to 2 times n plus 1, 3 to the n minus 5n, 3 to the n minus 1. So if you want, you could simplify this further, but this is sufficient to answer the question of what is f of n, or in other words, this is sufficient to solve the recurrence relation. So this is our final answer. Okay, so this gives you one example of how to solve a recurrence relation using generating functions. If you follow the same steps for many different types of linear recurrence relations, then you can often get the solution. Okay, so thank you for listening.